Welcome to the second week of the course Quantum Computing, Less Formulas, More Understanding, brought to you by St. Petersburg State University, the Faculty of Mathematics and Mechanics. On the previous week, we talked about the mathematical model of quantum computing and what demands it places on the physical process which implements a quantum computer. But we did not discuss the mathematical model itself and where it comes from. Today, we are going to start covering this topic. In my course called The Introduction to Quantum Computing, I introduce the mathematical model also on the second week. But I concentrate more on its applications, such as how one can design quantum algorithms using this model. I never explain why we use this model and not another. Understanding its origins requires some background in quantum mechanics. And I always promise my students that they don't need this background to pass the course. However, if we want to understand the physical nature of a quantum computer, we can't avoid at least a very facile overview of how quantum mechanics describes the world. You may think that the best way to give this facile overview is to invite a specialist in quantum mechanics to do it. That's what I also thought. I really spent some time asking experienced physicists different questions. And these questions seemed very natural and straightforward for me. But I never got an answer which would be as simple as my question. I also had the feeling that most of my respondents tried to avoid answering my questions and seeked the way to change the topic. The reason of this is quite obvious. Imagine you study physics for some time, say several years. You study Newton's laws, then Lagrangian formalism for these laws and why it is better than Hamiltonian formalism, then the mathematical description of oscillations and waves, then Maxwell's equations, and only then you are ready to approach the quantum mechanics. And after it, somebody comes to you, somebody who did not study all this, and he asks a simple, as he believes, question. For example, why do we need complex numbers in the quantum mechanical description of the world? Why can't we describe it just using real numbers? What physical meaning these complex numbers have? And you understand that to explain it, you have to start from the very beginning. And you definitely don't have time for this. Anyway, this is what exactly we are going to do. We are going to try to answer these simple questions without a deep diving into theoretical physics and even mathematics. Now you probably understand what kind of a tough target we are going to aim during these 2 weeks. The questions we are going to address are: first, what is a qubit? Why mathematically it is a two-dimensional vector? Then, what is the superposition state? And why it is the source of so-called quantum parallelism? Then, why do we need complex numbers? Isn't it simpler without them? Then, what is measurement? How the probabilities of the measurement outcomes are calculated, and why so? And how the system of several particles is described, and why do we need tensor product for this? And last, what are the entangled states? I believe that this list looks complicated to you now. Let's see what we can do with that.